This second video on MOSFET is on sample problems, so I'm going to randomly pick some problems, sample problems. So MOSFETs are very important components in modern circuitry. The processor, the modern Intel processor has, billions of transistors, which works as just the switches, turns on and off to make the logic gates, this processor, and the hundreds of thousands of these MOSFETs, microscopic, MOSFET transistors can be fabricated as an integrated circuit, not discrete circuit, as an integrated circuit with photolithographic technique. It's a very important. And here, this is the animation I have also included in my lecture slide. Shows the basic functionality of a basic action of MOSFET transistor at various bias voltages. In this video, I will be solving some sample problems on MOSFET, which stands for metal oxide semiconductor field effect transistor, which is the most modern version of the transistors. So here's the main formulas that you should know to solve the MOSFET transistor problems. This is also part of the formula sheet. So here's the IV characteristic of a MOSFET. Here's the MOSFET symbol. So MOSFET, any transistor is a three-terminal device. It has a source, drain, and the gate. So since we are dealing most of the time we are dealing with the N channel. This is an N channel, MOSFET symbol. N channel means the conduction takes place, through the thin layer of electrons here. So that's why it is called N channel. So go back and check my video series on MOSFET. So here, since electrons are the charge carriers here, that's why the electrons flow from drain to source, and the current, this ID, which is the drain current, can be significantly controlled by the gate voltage, how much gate voltage you put here. Okay, and here's the output characteristic of MOSFET look like. So this is the drain current versus the drain source voltage, drain source bias voltage at some fixed gate voltage, right? So, and you will get this kind of curve, not very non-linear. It has two distinct regions. One is the ohmic or triad region, almost linear, and in ohmic region, the drain current can be calculated by this model formula. And after some VDS, when VDS, the drain source bias voltage, is greater than or equal to the gate voltage minus some threshold voltage, when this is greater or equal to that, then the drain current doesn't really change actually with the increase in drain source voltage. So it just keeps just remains flat, and that region is called saturation region. And the drain current increases very little actually with VDS, and that the drain current then in saturation region is given by this formula. So there are two drain current actually. One is in linear region, ohmic region. One is in saturation region, and you can clearly see the drain current just depends on in saturation region. The drain current just depends on the gate source voltage, not the VDS. Okay, that's the thing you have to know. So these are the main formulas. So let me just get started uh, with some very simple one. So here's the one. So here's the MOSFET. This is the lateral view, cross-sectional view of a MOSFET transistor. It's a N channel. N channel has P body. There's this thin layer of electron layer here for transition. So this is the drain, this is the source, and these are the bias voltages given to you. Drain voltage is 5.8 volts with respect to source is at 0 volt, and gate voltage is 4 volts. So these are the given. Okay, so this width and length, this has to do with the gate. This is the width of the gate, which is this, and the thickness of this oxide layer, right, we call L, and this is width, right? Those are given, and these are the capacitance, and this is the electron mobility, which you don't need to worry about because we're just gonna use the formula. So it's asking what's the drain current in this bias voltage situation. What's the drain current through this, you know so if you want to draw the symbol in terms of symbol, you know it's just a three terminal device like this, right? It's just the transistor is just the three terminal. This is the gate, this is the drain, this is the source, and depending on the gate voltage it flows, and this is the direction of the p-n junction for the n channel, and this is the id. So it's asking what's the drain current, right, in this configuration. So then we can just get started. So here, so from the circuit, so first we're going to need all the bias voltages. So what is VDS is drain source voltage. Drain source voltage is 5.8 minus, so source voltage is 0, so 5.8 volts. So what is VGS? Because you're going to need all this bias voltage for drain current calculation. So VGS means the gate source voltage, again 4 volts minus 0 volts, so 4 volts, right? And this is given the threshold voltage. You're going to need at least 0.8 volts, right, as a gate voltage to open up the transistor. In order to get the drain current, you need at least 0.8 volt as a threshold voltage as a gate volt, right? So these are the given parameters. So since here you can clearly see, you have to check VDS is greater than VGS minus VT. You have to check these relations because this transistor could be in ohmic or triode region, right? Or it could be in saturation region. This is called ohmic or linear region. This is in saturation region because there are two different formulas of drain current formulas. So here VDS is 5.8, right? VGS is 4 volts minus 0.8 volts. So 5.8 is greater than 3.2 volt. So that means it's in. So first you need to figure out which region is this, based on the bias voltage. It's in saturation region, as you can clearly see, right? Because why? Because VDS is greater than this difference is clearly in. So when it is in saturation region, this is the drain current formula. It's very easy. It will be given K VGS minus VT whole square, right? So what is K? K is constant, and this constant depends on many factors, so you don't need to worry about that. This will be given to you. So constant K in this formula is this electron mobility, the capacitance of the gate, and the width of the gate, and the thickness of the gate. And you can put all these values, because these are all given. Okay, so I'm just putting all the given values. So 2.5 divided with 0.6, same unit. So K is this, okay, and just put it here. So I'm just gonna put it here. So K is 1 10 to the power negative 4. Gate source voltage is 4 volt. The threshold voltage is 0.8 volt, and there's a square. So ID, which is the drain current, so this transistor, right, through this transistor, the drain current through this channel, in channel, is 1 milliamp, just around 1 milliamp. So that's how you should solve. Okay, so this is the next problem. So this again, this n-channel MOSFET transistor is biased using two batteries. This is VDD, this it calls VGG, and it has two parts. So part A is here, this battery is 0.5 volt, which will bias the gate source voltage, and this VDD is 7 volts, which will bias drain source voltage, and it's acting was the drain current and all the voltages across the capacitor. So this is the drain current, right? And so first thing to know is, remember, the most important point is if the gate source voltage from here to here, gate source voltage, right, is greater than the threshold voltage, in this case is 1 volt, then transistor will be on. It will turn the transistor on, right? Then you have some drain current. But however, if VGS, which is gate source voltage, is less than the threshold voltage, transistor will not turn on. It will be on off state. That's the most important point. So we need to check this VGS. What's the gate source voltage here? So to check this gate source voltage, you can just use the logic or just use KVL, in this loop from here to here. So if I use KVL, it's gonna be VGG, right? So I'm just using KVL around this input loop, minus whatever current, if there is any current, RG, and minus from here to here, let's call it VGS, gate source voltage, because this is grounded, right? Is equal to 0, right? But this is 0 because why? Because IG is 0. That's the main point actually. The most important point in MOSFET is this transistor. The gate is completely isolated from the transistor, body, right? Because there is some oxide layer here, a good insulation layer, that will completely isolate the gate from the transistor. It will just provide the field to control the drain current. That's the most important part in MOSFET, and that's why the MOSFET has a very high input impedance that will isolate the input circuitry, from the transistor. Okay, so then that means your VGG is just VGS, right? So your VGS is just VGG. VGG is half a volt. And let's compare now. Go back to this. Which one does it satisfy? So your VT is 1 volt is given. However, your VGS is less than 1 volt. So it is gate source voltage is less than the threshold voltage. So that means the transistor doesn't conduct. Transistor will be in off state, right? Transistor doesn't conduct. So the transistor is off actually. This MOSFET transistor in this configuration for part A, we're solving part A, is off actually. Why? And your answer is ID is 0, right? And VGS, which we have just calculated, right? And VDS, since the transistor doesn't conduct, right? You can apply just KVL here. Since the transistor doesn't conduct, the drain source voltage will be exactly equal to the VDD, right? So it's just VDD, this is 7 volts. So this is your answer. This is what it is acting actually. It's acting all the voltage and currents through the transistor. Okay, that's the answer. So it has a second part. Second part is now what happened to the drain current and all these drain source voltages across the transistor. Now if you make this battery voltage 1.5 instead of half a volt from part A, now in part B, what happened to the drain current and the drain source voltage, right, if you make this bias battery 1.5 volts. So again we have to first calculate the gate source voltage. So in KVL here, VGG minus VGS minus V of S is equal to 0, but this is connected to the ground directly, so VGS is just VGG, right, which is just 1.5 volts, and you have the threshold voltage is still 1 volt. So since the gate source voltage is greater than greater than the threshold voltage, because here is 1.5 volts, 1 volt, so the transistor conducts. right? The transistor conducts, it turns on, transistor conducts, right? But we still don't know actually whether the transistor is in this region, right, or saturation region. We still don't know. We need to figure that out, and we need to do some assumption. Okay, so a transistor conduct, but there are two cases. One is if VDS is greater or equal to VGS minus VT, it's in saturation region, right? If the VDS, because this is VDS, this is ID, this is the output characteristic of the transistor. And second, if VDS is less than VGS minus VT, right, for the given voltage, this is an ohmic region, linear ohmic region. So we're going to test both. So first we're going to go with this first case. So we're going to assume that, we will assume that VDS is greater than or equal to this quantity, and we're going to find out the drain current based on this, because we know the formula, and based on that we're going to check if this condition is consistent or not. Okay, so we assuming the transistor is in saturation region. Okay, assuming that the transistor is so then we know the drain current formula, right? So in saturation region, the drain current formula is KVGS minus VT whole square, and K and everything is given. K is given 1.3 milli. It has some units. VGS is 1.5 and VT, which is threshold, is 1. So ID from here, the drain current is 3 × 10⁻⁴ amp. But we need to test it, right? Now, based on this ID, calculate VDS and test if it is if this satisfy this first condition or not. So let's test it. Okay, so go back to this, the output side. So I'm going to apply the KVL in this loop, output loop. So I'm just going to apply KVL, okay, to find V, because we need to somehow figure out the drain source voltage across the transistor. So if you just apply the KVL around this loop, right, so it's going to be and this is really easy. So I'm applying KVL, right? So it's gonna be VDD minus IDRD, which is given VDS, drain source voltage, is equal to 0. So VDS is equal to VDD minus ID, which we already know, and RD is also given. The drain, this resistor is also given. So VDD is 7 volts. The drain current we have just calculated here. The drain current, right, is 3 minus 4. The RD is 7 kilo ohm, 7,000. So that's given 7 kilo ohm. So once you calculate that, you're going to get 4.9 volts. Okay, and test. Let's check VDS. Let's see if this satisfies this condition or not, because we have calculated the drain current, right, by assuming that this is in saturation region. So let's test it. So VDS we have calculated 4.9 volts. VGS is 1.5 volts, right, and minus 1. So 4.9 volts is greater or equal to 0. So this satisfies. It's consistent with our. It is, right, with our assumption. That the transistor is in, is in saturation region. Okay, so that's your answer. So finally our answers are ID is 3 × 10⁻⁴ amp, VDS is 4.9 volts, VGS is 1.5 volts. So these are the answers it is looking for. Okay, so that's how you solve. So next question is, so the transistor is biased as shown in the figure. There this will bias the gate and this will bias the drain source, right? And it says at this bias position there's a drain current. The drain current is given to you 0.4 milliamp, right? And these are the resistors, and it's asking what value of this VG, what value of this battery or the bias voltage for the gate will uh, place the transistor at the edge of the saturation. So what does it mean, the edge of the saturation? So that simply means, if you again see the output characteristics of the MOSFET, so the drain drain current versus VDS, so it will have output characteristics. So this is the edge, right? This is the threshold, right? So this is the edge of the saturation region. So VD at this critical point, VDS is equal to VGS minus the threshold voltage. Okay, right? So it's asking at what value of the gate voltage, right? This VG will put this transistor in this stage. So we'll give you that much drain current, right? So that's the question. So then first we're gonna need gate source voltage, the voltage drop from gate to source, always from here to here. So how do you find that? So again, KVL here, right? So I'm gonna apply KVL around this loop. So it's gonna give you VG minus, from here to here you have the internal voltage drop from gate to source is we call VGS. That's what we're gonna find. And from here to here here you have a drain current. So the voltage drop from here to here is negative ID RS, which is 2 kilo ohm, is equal to 0. So I simply apply KVL in this input loop from here to here. So from here you can figure out VGS, right? In terms of VG we don't know, which is this battery voltage based on the question. So VGS is VG minus so ID is given. So is the drain current here is 0.4 milliamp and RS is 2 kilo ohms, right? So based on that is VG, which we still don't know. So let's keep it like this. We're gonna need that later. Okay. So VGS, which is the gate source voltage, which is the voltage drop from gate to source, is VG minus 0.8 volts, right? Which we're gonna need that. Now let's go back to this. Based on the question, it's asking is in this condition. So it's at this transistor is at the edge of the saturation. So it satisfies this condition, right? So when VDS is equal to that, then the drain current is already in saturation region, right? So the drain current is given by, again, this formula, right? Square. And from here, so ID is given 0.4 milliamp. So K is the constant for the transistor, which is also given 1.2 milli. And VGS, so you have to put in terms of VG, which is what we're solving, minus VT is it says VT, which is the saturation, the threshold voltage is 0.7 volt. This is square. Okay, so this will now solve this. So it's gonna give you something like this: VG minus 1.5 square, and this is a quadratic equation. Okay, so it's gonna give you two values. So if you solve this, it's gonna give you two values: 2.07 volts and 0.926 volts if you calculate the VG from this. So we need to figure out which one is the right answer. So we need to figure out. So let's begin with, if VG is let's see, 0.926 volt. If the VG, the battery voltage, is this, let's see what's going to be the VGS, gate source voltage. So VG, so based on that, if this battery voltage, right, is that small, let's say 0.926 minus 0.8, this is a negative value, right? And no, not negative, but a very small value. So that will keep, then this will be less than the threshold voltage, right? Because this gate source voltage turn out to 0.126, very little, right? Is less than 0.7. This will be, the transistor won't conduct, right? The transistor will be in off state. Transistor doesn't even conduct. So this is not possible, right? If this battery voltage if you keep this battery voltage 0.926 volt, the transistor won't conduct, right? And this is against our assumption that you have some drain current, right? So that's against the assumption. So that means our final answer, VG, has to be 2.07 volts. Okay, so that's your final answer, right? So this battery voltage, right, has to be 2.07 volts to get this much drain current, and that will put in this region. So next problem is something like this. So again, you have a n-channel MOSFET and it's biased like this. So this is a most practical way of biasing a transistor. This is how actually the transistor, any transistor, is biased using these voltage divider circuits, in real life, in the given circuits. So it's actually find all the current and voltages across the transistor. So it's asking what's the drain current, what's the drain source voltage, what's the gate source voltage, something like that. Okay, so to get started, we can assume that the transistor is in saturation region. Okay, because the drain current formula for saturation region, is really simple compared to the ohmic region, right? So we assume that we just began with this, assuming the transistor, the device transistor is in saturation region. Why? Because the formula is simple, right? When the transistor is in saturation flat region, it's the drain current is given by VGS minus VT whole square, right? And then you can try to solve the drain current, but you're going to need a couple of things first. So this VG, which is the voltage here, right, at this node, from the voltage divider, VG, which is the voltage here, is just the voltage divider, voltage across the 100 kilo ohm resistor, which is 100 divided by 100 plus 100 times 10 volt. Okay, so that's just the 5 volt, just the voltage divider, right? Because and then here KVL again, because we're gonna need VGS, KVL. If you apply KVL around that, so VG, right, which is the voltage here, minus VGS minus here drain current, right, is the drain current, same, the drain current here and here will be same, minus ID times this resistor, which is 6 kilo ohm, is equal to 0. I just apply KVL around this loop, and because I'm gonna need VGS, so VGS is VG minus ID times 6000. Okay, And VG from the voltage divider is 5 minus 6000 ID, right? VGS. But we don't know ID, so just keep it like that. All right, let's call equation number 1. Now you have to put this here, right here. Right, then ID, because we assume that the transistor is in saturation region, so we just use this formula for ID, the drain current, VGS minus VT, and these are all given. So ID, we're calculating that. K is the constant for the transistor, 1 milliamp, so then negative 3 given. VGS we have calculated in terms of ID, 5 minus 6000 ID minus the threshold voltage, it says 1 volt, that's given. The threshold voltage is given, so 1 volt, and that's the square, right? So you're gonna get, now if you simplify, is 1000 ID, because if you just divide this by this 1 milliamp, 1 milli, so 1000 ID is 5 minus 4 minus 6000 ID, right, square. And it's gonna so solving, so you'll get a quadratic equation. Solving this quadratic equation will give you two values of ID, right? The drain current. One is, so if you solve it, I have already solved it, 0.89 milliamp. The other value, second value, 0.5 milliamp. So how do you choose which one is correct? So you have to check, which value of the drain current will turn the transistor on. So you have to check VGS. Okay, check VGS. So let's say if ID is 0.89 milliamp, say, right? So then VGS, which is from equation number 1, right? 5 minus 6000 ID, right? Your ID is this, that much. So VGS will be negative, right? If you put that, and that's not possible, because the transistor will be in off state. If you bias, if the gate source voltage is negative, transistor will not conduct, right? So that's not possible. So your ID has to be half milliamp, 0.5 milliamp. Okay, you still need to do one more check. Okay, so your ID is 0.5 milliamp, right? So your correct answer is ID is 0.5 milliamp. But we still need to check one more thing actually. Check VDS. We still need to check this drain source voltage, because we before we even did this calculation, we assumed that the transistor is in saturation region. Now we have to prove this with this drain current. The transistor is in saturation region or not. How do you check? So check this relation. If the transistor is in saturation region, the drain source voltage, right, has to be greater than GS minus VT with this drain current, right? So let's check that. So first of all, let's calculate VGS. VGS from equation number 1, 5 minus 6000 ID, right? So 5 minus 6000 times ID is 0.5 milli, so then negative 3. So VGS, so you do that calculation. So VGS is 2 volts. Okay, so now next you're gonna test VDS. You need to test the VDS. What would be the drain source voltage? So go back to the circuit again. So you have to apply KVL from here to here, from higher voltage to the ground. Okay, so if I apply KVL from top to bottom here, so 10 volt minus this volt minus this volt minus this volt is equal to 0, right? So KVL on the output side here, from here to here, 10 volt minus ID times 6000 resistance minus VDS drain source, right, minus again ID, again the resistance is, again the bottom resistance is again 6000. So I just apply KVL, right, and then solve for VDS here, because you know the ID is these IDs are 0.5 milliamp, right? And you can easily solve for VDS, and if you solve for VDS, it you'll end up with 4 volt. And check this relation now. So VDS, let's see whether it satisfies this condition or not. VDS 4 volt, VGS we have calculated 2 volt, and the threshold voltage is 1 volt given. So 4 volt is greater or equal to 1 volt, right? So it satisfy the condition for saturation region. Okay, and our assumption that the transistor is in saturation region is consistent. So what would be your final answer? Your final answer will be ID is 0.5 milliamp, your VDS is 4 volt, and your VGS is 2 volts. So that's gonna be your very final answers, right? It's asking all these current and voltages on the transistor.